Hello everybody. I'd like to take a minute to show you this problem which I got right off of our assignment. It's from my math lab, and I'll let you read this top part, but you can pause the video if you want to do that, but I'm just gonna explain it in my own way. Okay, so we're given this formula which relates the surface area of a body, of a person, in square meters, in terms of their height and weight. Okay, and it would make, I could see how you could do that. I mean, I didn't know what this formula was before I saw this, but it makes sense that those things are related, you know. Okay, and I've got all these measurements and so on. Now, the first question that I see up here as I begin working through the problem is to find this derivative, the derivative of surface area with respect to weight. Okay, so that's called Leibniz notation, and that's how I'd read that. And it addresses this question about how surface area changes as weight changes. Okay, but notice that there is this other variable there, height, or it at least seems like a variable, right? In the beginning, it seems like weight and height could be different numbers, they could be variable, and then they give you surface area. But in terms of this derivative, that bottom part, dw, tells me that w is a variable, but all other factors in that equation are constant. Okay, s is the dependent variable, and w, at least for this derivative, is the independent variable. By implication, this other aspect, this other factor, height, is constant. Okay, that's what that means. Okay, so when I see this, whatever that variable is down there is the variable in the equation, and if there's anything else there, other factors used in calculation or whatever they are constants. Okay, all right. So w is the variable. If I see h anywhere, if I need to think about how to apply the rules of calculus, I have to think of h being a constant. Okay, so that's how we use that notation, and that's how the implication there is that h is a constant. So when I find this derivative, I'll use the rules applied with h being a constant and w being a variable. Real quick, sometimes we write Leibniz notation like this. Like I'll say, okay, here's what I'm doing. You want the derivative of s with respect to w. I'll take the derivative with respect to w of this. So this is another way that Leibniz notation is sometimes written. It just says that here in this step, I'm taking the derivative of that formula with respect to w. And that means, like I said earlier, that in that formula, w is the variable and h is a constant. So I'm treating h like a constant. You know, the rules of calculus are different for variables and constants. So the way I would do that is I would use the chain rule, because there is, a function inside of this root. So first I rewrote the root as the 1/2 power. And then I put w times h inside of that. So I would go like this. Here's how the chain rule would work. I'm going to carry this 1/60 into my answer. This power would be written there as a coefficient. I would subtract 1 from this power, and then I would multiply that by the derivative of that inside part with respect to w. What goes here with the chain rule is the derivative of w times h with respect to w, meaning that that h is a constant, and that is h. Okay, it's sort of like if you're saying, what's the derivative of 4x? It's 4. Okay, what's the derivative of 11x? It's 11. It's like that. So the derivative of w times h, considering that w is a variable and h is a constant, is h. Okay, so I get that, and then I can combine some obvious things here, like 60 times 2, that's 120. I get 1/120. And then I can just combine this into one big fraction. I got an h on top, and I can send this root down there under the bar. That negative 1/2 becomes positive 1/2, or square root of w times h. So there's your derivative, ds over dw, the derivative of surface area with respect to weight. Okay. All right. Now, after that, I noticed that I'm given like a particular height. Now, about that, I'll say height was assumed constant from the beginning. Like if this is the derivative that I'm considering or working on, then it means that w is a variable and h height is a constant. So height was assumed constant from the beginning. Right? That's just how this derivative is understood. That's what it does. It assumes h is a constant. And then it explores, how do weight and surface area change together? And I mean, to me, that's the only way it makes sense to think about this. I doesn't really seem to make sense to think about how weight and height and surface area all change together. It's like we got to hold something fixed and change one thing and see what happens. So if like somebody's height remains constant and their weight goes up or down, then yeah, I can see that their skin's going to have to stretch or something like that, right? The surface area of their body is going to have to change if you hold the height constant, okay? So I kind of get that. Yeah, you hold the height constant, you get heavier. Yes, your surface area will change as a result. So yes, okay, the height's held constant. That derivative, it just implies that. And if you tell me, okay, here's what the height is, we told you it was a constant, but we didn't tell you what it was. We just told you it's not changing, and you treat it as a constant, but we're not going to say what it is. Now, if you tell me what it is, then okay, I can put that in to my derivative, and I get 174 over 120 root 174w. I don't think that there's anything meaningful to do to simplify that. You could rationalize this bottom part, but I don't really think that would make it simpler. So I'll leave it like this, and then that answer is acceptable on MyMathLab. What about the units? The question about units may come up. What are the units for that derivative? It's telling me how surface area responds to a change in a person's weight if the height is held constant. It has units of S over W. So your units here are the units of surface area over the units of weight, whatever those are. So if you wanted to know the units of this, you would say it's area over weight. Okay, it tells me your weight changes by whatever measurement, and your surface area of your body will respond by changing by this bit. But it's area units over weight units. Those are the units of this. In general, for any derivative in Leibniz notation, the units will be the units of the variable on top above the units of the variable on the bottom. Okay, so it's area over weight for S and W. Okay, now this last question is, well, can you tell me, like, the big picture, does surface area increase more rapidly with respect to weight at lower or higher weights? So I can see it being different. Like, if somebody has a very low weight and they gain weight but stay the same height, then maybe their surface area of their body has to increase in a different way than if they were already much heavier. Okay, so I can see that, well, this number might not be the same all the time depending on what your weight happens to be. Okay, so whatever your weight is, if you get a little heavier, yes, the surface area will have to also increase. Okay, but exactly how much might depend on how much you weigh to start with. Now, when I look at this formula, here's what I notice about it. I see that W is in the denominator. And I know just by arithmetic that when you divide by a small number, you get a big answer. But when you divide by a big number, you get a small answer, right? That is just arithmetic. 1 divided by 2 is bigger than 1 divided by 20, for example. So I would say, like, well, here's the big trend, the overall trend with this derivative. For small weights, that derivative will be large. This number will be large. And that tells me S is increasing more with respect to W. Okay? Because this derivative tells me how S responds to changes in W. And if W is large, then this quantity will be smaller and the derivative will be smaller. Okay? And that means, okay, the derivative is smaller. The derivative tells me how S responds to changes in W. So S is increasing less with respect to W or weight in that case. All right, so I can see whether W is big or small, that the derivative is big or small, and it tells me how S is increasing either more or less. All right, with respect to W. Now, that's my thinking of it, and it all comes from the just bare arithmetic that when I divide by small numbers, I get a big answer, but when I divide by big numbers, I get a small answer. Now, of these statements, I got to pick the one that matches what my thinking was on this, and it's the last one. S increases more rapidly with respect to weight at lower body weights. Yeah, because, I said if W is small, that's a low body weight, then this number will be comparatively bigger, and it tells me how S responds to changes in W. Okay, all right, so yes, at lower body weights, and then because the rational expression with a smaller value and the denominator has a larger value, so that's my way of saying if I divide by a small number, I get a comparatively bigger answer than dividing by a big number. All right, so that's all parts of the question. With my own thinking and analysis along with it, I hope you see how it matches up to all my answers on my math lab, and that you would ask questions if necessary.